Hello everyone, myself Soumya. I am working as assistant professor under TEQIP 3 in Assam Engineering College. Under our GATE initiative in the subject power electronics, already many topics have been discussed. For example, different type of power electronic switches and their characteristics. Next, different type of power electronic converters have been discussed. For example, AC to DC converter or rectifier, DC to DC converter or chopper. Today, I am going to start the discussion on the topic DC to AC converter or inverter. Okay, now let us find out what are the subtopics we are going to discuss here. So now in the topic inverter, first we are going to discuss the need of the inverter and its applications. What are the applications and why do we need inverter in the application? Then we will discuss the types of inverter, how many types of inverter in use, those things we will discuss. Next we will discuss the inverter and its operation, how we operate an inverter, what is the operating principle or the working principle, that things we will discuss. Subsequently we will discuss single phase inverter, three phase inverter, both voltage source inverter and current source inverter. Specifically for voltage source inverters we will discuss 120-degree mode of operation and 120-degree mode of operation. Those two we will discuss under three phase inverter. Then we will discuss the Fourier analysis of these inverters, and finally we will discuss the pulse width modulation. Why do we require the pulse width modulation at all for inverter operation? Those things we will discuss, and finally we will conclude with the discussion of previous years, some question, GATE question paper from previous years. Okay, so let's start. So first, why do we need inverter? Okay, we need inverter because there are certain type of source which provides power in the form of DC, in the form of DC voltage or DC current, DC voltage and DC current. Okay, so what are these sources? The sources are suppose PV panel, suppose fuel cell and battery. So the battery is not a source purely, it is a storage. Initially we have to provide power which will be stored, and at the time of requirement the battery will provide power. We have to provide power to the battery for storing purpose, then battery will store the power, and then the stored power will be delivered from the battery to the load. So in that sense we can consider as a source of DC. So etc. This type of some DC sources are there, and there are certain loads where we require, most of the loads we require AC. Okay, or certain loads are there, or the some appliances are there which runs in AC. Okay, so the AC may be single phase AC or maybe three phase AC. Okay, but we require AC. So what are the examples? For example, induction motor, induction cooktop, air conditioner, etc. So we can see there are certain sources which produces DC, and there are certain loads or the appliances which require AC. Okay, so what happened here? There is a mismatch between the source and the load. That means the type of the supply which source provides and the type of the supply which load requires. The source provides DC and load requires AC. Therefore, there is a mismatch. So definitely there should be something which will fulfill our need. Who will fulfill this need? That is the DC to AC converter, or the DC to AC conversion is required so that we can use the AC appliances or the load where we have the DC supply. Okay, so now you may ask us, is there any devices or anything which is there which serves this purpose. So obviously the commutator of a DC motor, suppose in a DC motor we have the commutator. This commutator does the similar type of job, but there are certain problems associated with the commutator, which has been already discussed in DC machine specifically, which are discussed in the DC machine. And this commutator is quite old technology where the loss is more, just quite lossy. So efficiency is less. So what are the problems? If I say there is this problem of sparking, there is a frequent replacement, requirement of frequent replacement of the brushes, and we require frictional losses. So therefore efficiency is low. Now definitely the power electronic static devices, as this is rotating in nature and this is static in nature, obviously it provides better efficiency. So power electronic converters does the same job with better efficiency, but there are certain problems. The problems are that the complexity of the control is more. It is a complex control. Complex control is required here. In addition, there is an issue with the issue of harmonics, but there are certain pulse width modulation techniques which deals with this harmonics. So therefore complex control is an issue, but there are a lot of advantages. That is, primarily there is a efficiency is less, sorry, efficiency is more and loss is less. So therefore we opt this solution nowadays. Now what are the applications? There are a number of applications where this inverter is used. In his first application is that UPS, what we use in our household. Whenever the power supply from grid goes or there is a power outage, at that time we require UPS. UPS provides the supply. How it provides? There is a battery bank inside the UPS which stores energy in terms of DC. Okay. Now whenever the power goes up, this energy stored in the battery supply to the household or the load, that is mainly AC in nature, that mainly requires AC supply. So the energy stored is DC and the requirement is AC. Now who fulfill this mismatch? The inverter. So there is an application of inverter. Inverter is also applied in electric motor drives, particularly suppose induction motors, speed control of induction motors, or suppose synchronous motor. In that case we use inverter instead of earlier days or old days register or rheostat based control, speed control mechanism. Nowadays we use inverter based speed control mechanism. There are certain other applications which are refrigerator compressor where used requires AC, inverter, and induction heating. In induction heating, the frequency which is required is quite higher than the supply frequency. Therefore we need from the supply frequency to DC and then DC to again higher frequency AC. So in between we require inverter. In addition, we require utility grid application, for example high voltage DC transmission system, which is also called HVDC. Also it is used in flexible AC transmission system, or it is also called FATS. So these are the utility scale applications. In renewable energy applications, we need inverter. For example, solar, where it provides DC, we need to convert to the AC, we require inverter. Here also in fuel cell, which also provides DC, now to convert this DC to AC, we require inverter. In addition, nowadays electric vehicles are coming up. In electric vehicles, the energy stored in terms of battery, in terms of DC in battery. Now the drive which rotates the vehicle or which moves the vehicle, that works in AC. So therefore we need inverter to control the speed of the motor which is used for the drive of the electric vehicle. In addition, there are certain applications such as microgrid, smart grid, etc. There are a number of applications where we use inverter. So now let us understand what are the types of the inverters. How many types of inverters we use? So based on input supply, what are the supply or input we give to the inverter, based on that we divide into two types of inverter, that is voltage source inverter and current source inverter. If the input to the inverter is the stiff DC voltage, then we call that inverter is VSI. We call that inverter VSI or voltage source inverter. Now if the input supply is constant stiff current or the current source, then we call that current source inverter or CSI. Okay. Now based on the output we require, if we require single phase AC at the output of the inverter, then we will use single phase inverter. If we require higher power range rating or higher power range, in that case we have to use for the three phase inverter. Okay, so based on that it is divided into two: single phase inverter, three phase inverter. Then based on the operation, it can be divided at the square wave inverter and pulse width modulation inverter. Okay, so we will discuss this type of inverters throughout the discussion. In last 4 to 5 lectures we will discuss about this. So let us start. DC to AC conversion. Now so what is available to us is DC. What is available to us is DC. Let us consider this is the fixed DC voltage with VDC is the voltage which is available to us. Let us draw it. So this is the voltage source with voltage VDC. Now what is required? What is our requirement? Our requirement is AC. Suppose say we require 50 Hz AC supply from the DC. So how to convert it? That we will discuss now. So suppose say we have an AC load. We have an AC load. Okay. This is AC load 50 Hz supply. Suppose it is required 50 Hz supply. Okay. Now how we can generate from this DC to AC? So what we can do? Now whenever we talk about the 50 Hz, what is the time period? Time period is 1 by 50, that is 20 milliseconds. So if I draw it here, that is the output AC voltage. This is the input and this is output we require with the 50 Hz. So obviously the what will the total time period? Total time period will be 20 milliseconds. This is time in millisecond. This is output. Now, so let's say this is also in millisecond. What will be the half cycle? Half cycle will be 10 milliseconds. Now what we'll do to generate AC out of DC? First, let us connect this directly to the load. We are connecting the source directly to the load first. Then what we will get it? We will get voltage of VDC at the output. So this is the V output. Suppose say this is the V output. What is the voltage output we will get? We will get VDC if we connect directly. Now after half cycle, after 10 millisecond, if I interchange the connection, that means this is plus, this is minus. Now if I connect this one to this and this to this, if I connect this way, then what is the output we will get? We will get minus VDC. So if after 10 millisecond, if I change, then what we will get? Minus VDC. Okay. Then again after this, if we change to the direct connection, we are connecting now again directly, then what we'll get? We'll get plus VTC, and this will continue. We'll get again plus VTC, and this will continue. So basically what it is generating? This is generating as an alternating voltage. This is generating an alternating voltage. So what we have done here? We have directly connected direct connection to the source and load for 10 millisecond, and we have interchanged the connection if I read the connection. So first direct connection for 10 millisecond and interchange the connection, that means reversed for remain next 10 millisecond. Okay. Then what is the output we will get? We will get a periodic waveform, and thus periodic square wave we will get it, which is alternating in nature. This is positive voltage, this is negative voltage we are getting. So we are getting alternating voltage which is periodic in nature, which is square wave, not sinusoidal. But we know that as it is the periodic waveform, if we do the Fourier analysis, so what we will get? We will get fundamental frequency f1. We will get sinusoids of. We will get sinusoids of what? Of fundamental frequency f1, and along with that third harmonics, that is the 3 times of f1, 5 times of f1, 7 times of f1, and continues. So you can observe that intentionally I have not mentioned about the 2f1, 4f1. So why I have not mentioned this one, you will see whenever I'll do the Fourier analysis. So basically if this is the f1 is the 50 Hz signal we want, so we will get the sinusoidal of 50 Hz. In addition, we will get sinusoid of 50 Hz plus what we will get? We will get the sinusoids of 150 Hz, sinusoids of 250 Hz, sinusoids of 350 Hz, and so on. So we will get sinusoids of these frequencies. So what we have to do it? We have to filter out these frequencies. We have to eliminate these frequencies to get the sinusoid with the fundamental frequency. That is what our ultimate aim or ultimate goal. Now to achieve this, we have to filter out the others. Okay. So basically now you can see. So what is required now? We require here a switching network. A switching network. Which can connect the load directly for 10 milliseconds and connect the load reverse direction for next 10 milliseconds. So now what will the output we will get? We will get a pulsating square wave. Sorry. This is the waveform we will get at the output. Now this output contains number of harmonics. So what we have to do it? We have to filter out. So we need a filter before connecting to the load. What is the job of this filter? To eliminate these harmonics. So if for higher order harmonics, the design of the filter is quite simple or easy, but for the lower order harmonics, it is a bit difficult. Anyway, for the time being, we are assuming that the filter will eliminate the harmonics. So what we will get? We will get the sinusoidal, which is our requirement. Okay, the 50 Hz. So our input, initially we have started with the DC voltage VDC, and finally we are getting a output with AC output with 50 Hz frequency. Okay, we can change the frequency accordingly, we can design it. So now our main focus will be the what is in the switching network, how we are achieving this, what is inside the switching network which is giving us to achieve this one. So you can see that within 10, after 10 milliseconds we have to switch. First we will connect directly, then we have to interchange the connection. After every 10 milliseconds we have to interchange the connection. So we have to do it very fast. Okay. This will be very difficult for our mechanical switches to change this interchanges so fast. Okay, because mechanical switches are laggy. Therefore, we require the switch which is the power electronic switches, what we have studied earlier. Those things will be required for fast switching, because the power electronic switches have the capability to switch very fast. So now let us understand the switching network which gives us from the DC to square wave AC. Okay, so let us see this. So let us understand the switching network first. So what is available to us? That is DC voltage. Okay, really simple, DC voltage available to us. Now let me extend this. I'm just going to design the switching network, how we can achieve this. So this is positive DC bus, this is the VDC voltage, positive DC bus, this is the negative DC bus, this plus minus, this is called the DC bus. Now we will, before going to the power electronic switch, let us understand what will be the characteristics of the power electronic switch. To understand that, first start our journey with our generic switches. Okay, here we will start with our generic SPDT switch. What is this? Single pole double throw switch. This is the pole, this is the throw T1 and throw T2, this is the pole P. Okay, now similarly let us draw one more here. This is another pole. Suppose this is switch 1, this is switch 2. pole of switch 1, pole of switch 2. So this is also T1 and T2. Now if I simplify this one, this will be T11 and this will be T12. So throw 1 for first switch. Now this will be T21 and this will be T22. Throw 1 for switch 2 and throw 2 for switch 2. So this is single pole double throw switch. Now let us connect the load here. Now let us connect the load here next. P2 here. Where we will connect it? Let us connect the load in between. Okay. Now let me change the color. So let us first, this pole is connected to through T11. Now pole is connected to T11 and suppose that this is connected to pole 2 is connected to T22. Now what will happen? This is plus and this is minus. What is the V load voltage? V output. What is the output voltage we will get? We will get, because the direction of the current will be this one. This is the direction of the current at present. For simplicity, let us understand the load is resistive load. If the load is resistive load, then this is the current. Now what is the voltage? This is plus VDC we will get. Okay. Now suppose if I change the position, this one, then what will the output voltage we will get? We will get minus VDC. We will get minus VDC because the positive terminal of the load is connected to the negative terminal of the DC, and the negative terminal of the load is connected to the positive terminal of the DC. So obviously the switch cannot be connected to the both either this position or this position, any one. Okay, so we can see P1 can be either connected to T11 or can be connected to T12, not both. Okay, so there is, you can see there is a complementary fashion. Their connection is in complementary fashion. If T11 is connected with P1, then T12 cannot be connected. If T12 is connected, then T11 will be connected. So this property is very important. We'll use that one later on. Similarly for this one also, if P2 is connected to T21, then it cannot be connected to T22, and if it is connected to T22, then it cannot be connected to T11. Okay, so this is how it operates. So first what we did for this one, that means we have connected P1 to T11 and P2 to T22. Next what we did, P11 is connected to T12 and P2 is connected to T21. Okay, now what is the output we are getting? If I draw it, this much is not required. Okay, for first half cycle we are getting plus VTC, and then remaining half cycle we are getting minus VTC, and this continues minus VTC. Okay, so now What we have seen, the two switch, if we connect, then we can get this one. For the, if I get the set 1, the connection set 1, this is for set 1, for connection set 1. This is for connection set 2. Set 2. Now, any other option available? Yes, there are two more set we can connect. Set 3 and set 4. What will happen? Now, suppose say, let me change the color, it will be easier to understand. Now, suppose if I connect both to the top throw, what will happen? The output will be 0. Or else, so what is the connection? P1 is connected to T11 and P2 is connected to T21. Similarly, in other case, if I connect this way, both are at the negative bus. If I connect both with the negative bus, either both with the positive bus and both with the negative bus, output voltage will remain same. Both the case we are getting 0. So in that case, P1 is connected to T12 and P2 is connected to T22. So both the cases basically we are sorting the load. We are basically sorting the load or making the load short circuit. So if there is any current present, any energy stored here, that will be basically free-wheeled. Okay. So specifically whenever we will use inductor, in that case this may be required. This connections will be required. Maybe useful. So now, so what we have seen, this is the structure of the inverter. This is the structure of the inverter. If we neglect, for the time being, we are neglecting the filter circuit. If we neglect the filter circuit, this is how is a switching network of an inverter. Now let us understand the characteristics of this one, of the switch. Let us understand the characteristics. That is the conduction and blocking. Conduction and blocking. Suppose whenever this is the connection, that is the set 1, whenever the connection is in set 1. Now what will happen? This is sorted. Okay, this is sorted. So what is this polar? This one? This is plus and this is minus. So this part, these switches have the capability to block, in this case, that is the VDC, positive VDC. Okay. Now here this is blocking the positive. Now if this is plus, this is sorted, this is minus. So this will also block the positive VDC. So under this condition, these two portions will block the positive voltage. Now what is the conduction under this case? So obviously the current will flow from positive this side to this side. This is the conduction. Now this depends on the load. If the load is resistive, please understand, if the load is resistive, then what will be the current? The shape of the current, suppose say this one is the shape of the current, that will be same in phase. The current will be in phase with the voltage. Current will be in phase with the voltage. Suppose say IO, that is VO, this is time. Suppose say you can say millisecond, or if I represent it in terms of angle, we can represent it in omega t. That's a fundamental angle. Now what we can see, that it is in same phase. Now if the load is highly inductive in nature, or RL load with inductive dominance or inductive nature, then what we will get? The load current will be, suppose say it is having some initial condition, or it may be start from 0 or this negative value to some positive value. This is the negative value. Suppose say this is minus I naught to this is plus I naught. I naught is the output current. So this will be the current through the load when this is inductive in nature, highly inductive in nature. Now if you observe here, we can see that for particular the set 1, under the condition of the set 1, we are getting both positive current and also the negative current. So we are getting positive current as well as the negative current. So the current direction in the load is bidirectional in case of, so direction of the current is fairly dependent on the type of the load you use. Now most of our load is RL type of load, so basically we will get bidirectional current. So the current through the switch will also be bidirectional in nature. Current through the switch will also be the bidirectional in nature. Okay. So bidirectional current conduction and unipolar, one polar polarity, unipolar voltage blocking. Now let us check the set 2. This is set 2. Now what will happen? Similarly here also, if R load, if this is R load, then what will be the direction of the current? Direction of the current will be this one, this, and this is the direction of the current. If I change this color to explain the direction of the current, so this is the direction of the current for R load, but if it is RL load, then it will be bidirectional. Now what is the voltage blocking capability switch has to be? This will be the plus and this is connected to the minus, so this will be same VTC, and here also this is connected to the plus, this is minus VTC. So unipolar voltage blocking capability and bidirectional current conduction. So if I draw it here, if I draw the characteristics of the switch, so this is the blocking voltage blocking, positive voltage, it is blocking the positive voltage only, and conduction is both, so this is V, this is I. So this is the characteristics the switch possesses. The switch. Okay. So bidirectional current conduction capability and unidirectional voltage blocking capability. This is the characteristics the power electronic switch has to be. Now let us check the what will be the power electronic switch pattern. Now let us erase this part and here understand the switching pattern. Now if I draw the same switch, this is IGBT with anti-parallel diode. This is IGBT with anti-parallel diode. Now if I mark the 3 terminal, can we not say this is the, suppose pole, and this is T1 and this is T2. This is pole P, this is T1 and T2. Okay. How we can say, suppose if we provide the gate pulse here, if we provide the gate pulse, what will be the direction of the current? Direction of the current will be this. Whenever we provide the gate pulse here, either for switch S1 or switch S2, then we will get this is the direction of the current conduction. Now when it is off, what will be the direction of the current conduction? Suppose opposite direction currents can be conducted through the diode. Now what is the blocking polarity? This will be plus, this will be minus. Now when this is not gated, the transistor and as well as diode can block the voltage with this polarity only. Okay, so we can characterize this SPDT switch using a power electronic, a leg of power electronic switch. This is called power electronic switch leg. This is a leg of power electronic switches. There are two power electronic switch which mimics the characteristics of a SPDT switch, which is a generic switch. Okay. So now if we replace this one here, what we get? That we will see now. So let us erase this part. Instead of SPDT switch, we are going to replace this one by power electronic switches. This is the gate where we provide the gate pulses to turn on the switches. Now here, similarly, we are going to replace this one by power electronic switch. With anti-parallel diode. IGBT, this is basically IGBT with anti-parallel diode. Thyristor also can provide these characteristics. If we go for the transistor or IGBT, so now this is the pole which is connected to the load. So this is a single phase inverter where now I have already mentioned that suppose this is, let me change the color, suppose this is switch 1 and this is switch 2 of leg 1 and this is switch 3 and switch 4 of leg 2. Now the gating pattern of these switches are complementary in fashion. What is the meaning? Meaning is that if this is the gate voltage we are applying to this gate, so obviously this is 0 and this is 1. Now the gate voltage which will be applied to the switch 2 will be in complementary fashion in nature. When it will be 1, this will be 0. So whenever we are giving 1, that means this is turned on. Whenever giving 0 means turned off. Okay. So whenever the switch 1 is turned on, the switch 2 will be off. Whenever the switch 1 is turned off, switch 2 will be on, and vice versa. So this is the gating pattern. So this is very, very important. We have to keep in mind. We can never turn on both the switch of a leg simultaneously. We cannot, because this concept I have already explained in case of SPDT. So you have seen, if we are connected the pole to the throw 1, then throw 2 will be open. If we connect the pole to the throw 2, then throw 1 will be open. Similarly, if we turn on the switch 1, the switch 2 will be open, and vice versa. So that is how we operate, and we get the AC out of DC. So this is the operating principle of single phase voltage source inverter. So what is the direction of the current? Obviously bidirectional current carrying capability. Through IGBT, the current flows through this direction, and this is the opposite direction. Obviously, whenever S1, if I say for set 1, whatever the connection, set 1 and set 2. Set 1, S1 will be turned on, S4 will be turned on. These are the on these two switches are on. What are the off switches? What are the off switches? Off switches will be obviously S2 and S3 will be off switch. Similarly here, what we can get, what will be on? So obviously S2 and S3 will be on. What will be off? The off switch will be S1 and S4. These two will be off and these two will be on. So under this condition we will get plus VDC. Under this condition we will get minus VDC at the output. Now after the Fourier, after filtering out, we will get the sinusoidal. This operation is called the square wave voltage source inverter operation. So thanks.